Good afternoon, everyone. Today we are actually going to present a complete new feature in Eclipse Kura that we call it Kura Wires. And before we present, I would like to introduce myself first. My name is Amit. I'm a student at Technical University of Munich. And for the past few months, I've been involved in doing my master thesis research work on Kura Wires. And along with me, we have a software engineer from Eurotech. You'd like to introduce yourself?
Yeah. Hello, everyone. I'm Matteo Maiero, and I'm a software engineer at Eurotech, and I'm also an Eclipse Kura committer. So let's go through the agenda of today's presentation. We will have a brief overview of our company, and then we will go through the IoT challenges that we think that Kura and the Kura Wires will be able to solve. So we will go through Kura and trying to see how it encapsulates complexity, and then Amit will go through Kura Wires, giving you some more insight description about what is in there. Finally, we will have a demo showing with a PLC and a proper device how our Kura Wires stuff works. So Eurotech is a company that has a big experience in terms of machine-to-machine and embedded computers. And we are developing for verticals that can be industrial, transportation, defense, and healthcare. But we are also really involved in open source, so we are part and active members of Eclipse IoT group. We are contributors of Kura and Kapua, that are two projects that were made taking the foundation on ESF and EDC, that are the two commercial solutions, and we are members also of the OSGI Alliance. So Industry 4.0, we face three big industrial revolutions, from steam, electricity, and then with computer and automation. And now we are approaching a fourth industrial revolution about connectivity, so having factories connected together and having sensors. But when approaching this problem, we will face IoT challenges related to fragmentation, complexity, and lock-in. Fragmentation because there are different sensor protocols and different time where these, for example, factories were built, and we have CAN bus, Modbus, OPC UA that have to be interfaced. We have different hardwares, but also different standard organizations that produce standards maybe for the same things, and this increases the mess of managing all of them. We have different protocols also to cloud, so we have MQTT, Lightweight 71, COAP, and this makes the complexity arise because we have such heterogeneous environments where the integration is really difficult. Also, the security is an important problem that arises the complexity because, especially in an industrial world, there are strict requirements in terms of how the data is managed and transferred, and who takes this data and manages it. And for the reliability in industry compared to consumer market, we have more strict requirements that have to be satisfied. Also for maintenance and lifecycle management, we have problems of deployment and installing upgrades and provisioning of new devices that have to be placed. So we are in a sort of lock-in problem due to these factors. And when developing a solution, you will end up with a structure like this. You have your factories with the sensors or actuator or PLCs that you want to connect some way, so you try to find out some gateways that can connect to those sensors, but then you have at the other side the business applications that need to receive data from these devices that are spread around the world. So our idea to solve this set of problems is to sustain and contribute to open standard and solid architectures, and we contributed with two projects in order to simplify the problem of IoT and splitting it into simpler problems at the field level with multi-service gateways that are running Kura and are able to communicate with sensors and PLCs and grab this data and send it to an IoT integration platform that can be, for example, Kapua, that is the endpoint for the communication for the gateway, but is also an endpoint and a single endpoint for business applications that have to retrieve the data and process it. Today we will talk. Amit will talk about the lower part, the field part, so the Kura stuff. So Kura, as you probably know, is an open source Java and OSGI-based application framework container that tries to simplify the design, the deployment and the management of embedded applications, providing a way to have modular applications on top of the Kura structure, leveraging the features of Java and OSGI. We are also abstracting the hardware, so you don't have to deal with that, and the field protocol libraries. So those are building blocks that you get when you get Kura. We have also tried to simplify the cloud connectivity, so for remote management of application and device, and we are trying to provide correct development tools that ease the work of the developer in order to create the final solution. So the main purpose of Kura is to try to encapsulate complexity, because if you buy your Raspberry Pi or the Intel Edison, you get only the hardware and the Linux or the operating system layers. But then on top of that, you have to develop your entire application. You have to deal with the connectivity. You have to deal with how to perform remote management, maintenance. And then at the end of that, you have to deal also with the creation of the vertical application. But the competencies that you need to develop such an application are really, really hard to achieve, because you need people with different competencies, with different experience, and also the time to market is really increased. So you can simplify a little bit your work using a Java virtual machine. So you write in Java, you don't have to deal with the building and managing for a different platform. But again, it reduces the effort, but not so by much. So our idea and our proposal is to use Kura, that is a complete framework that provides you some building blocks that should simplify, on top of OSGI and Java, the working and the creation of your vertical solution. So the amount of work that you need to create is reduced, and also the competencies and the time to market that are required to develop such an application are few. I can give you an insight about the current Kura layer and structure. So we are based on Java. We are supporting Java C 6, 7, and 8 currently. And we then on top have an OSGI application container that currently we use Eclipse Equinox. Then we have the device abstraction layer that allows you to communicate with the serial devices, with USB devices, for example, to access to the GPS position, and communicate with Bluetooth 2.1 or 4.0 BLE devices. Then we have a layer of basic gateways services. We provide, for example, a DB service, a wrapping of HSQL DB that allows you to, that manages the in-flight messages, but also allows your application to store their data locally. We have a support for Watchdog, both software and hardware. And then we have another layer for network configuration that allows you and simplifies the process of configuring the device in terms of connectivity, so for the cellular or Ethernet connection, but also simplify the work of configuring the firewall and the port forwarding, so it's not needed so much competencies to do that. For the connectivity and delivery layer, we are wrapping an MQTT library, PAO in this case, and we are providing a set of APIs that can be used by the application in order to easily communicate with the cloud platform. We have a block for remote management where you can manage the configuration for remote of the specific device, perform updates, but also perform remote access. We have a layer also for field protocols. We are providing currently support for Modbus and CAN bus. And we have finally an administrative graphical user interface that you see here, and that perfectly matches and maps the features available. So it simplifies the configuration of your solution, and you don't have to have people experience in order to configure, for example, the firewall, because it's really, really simple. Your application will be running on top of this stack and will get all the advantages of the underneath layers, and will be configurable as an application by the web UI. Okay, so this is an introduction of Kura, so maybe Amit, you can start with Kura Wires.
Hi again. So, so far,
This one?
no, that's fine.
What is this?
Yeah. So far, we have already seen the different benefits of Eclipse Kura, and we have also seen that how it is useful to have such kind of service gateway model and such kind of framework which facilitates you with all the advantages to have your own IoT application in a pretty effective and pretty easy way. But there are also lots of people out there who have completely different needs. So for them, they think that, okay, Eclipse Kura seems pretty powerful for them, for their proof of concept. And all of a sudden, they also think that, oh no, they have to learn Java and OSGI to learn, like to develop a configurable application in Eclipse Kura. So it's really difficult. So now the problem arises, and for us, the problem statement that we wanted to address is, how can I develop my proof of concept using Eclipse Kura, leveraging all the functionalities of Eclipse Kura, even pretty easily. So without learning Java and OSGI, without writing any single line of code. So that's the problem statement we actually wanted to address. So how do we address this? So the way we actually, the approach that we have taken so far is the data flow programming approach. So this data flow programming model is actually widely used in this wireless sensor network applications. And this kind of data flow programming model, in this data flow programming model, the application logic is actually expressed as a directed data flow graph, where you have the nodes. Nodes can have inputs, node can have outputs, it can have both. And also along with this, it has the independent processing unit. So every node, they receive input, they process it, they produce outputs for their connected or wired nodes, downstream nodes. So that's what every node is responsible for. And apart from it, it's also highly reusable and portable. Why do I mean by that? Because each and every node doesn't affect the processing of, like the execution of other nodes. It's actually responsible for doing its own work, what it is responsible for. It doesn't hamper the work of the other nodes. Moving on. In Kura, we have incorporated the new feature called Kura Wires, which actually conforms to this data flow programming model. So in the context of Kura Wires actually offers a significant advantage by raising the abstraction level, I would say, and it also eases the developer's task without sacrificing much flexibility. What do we mean by that? So you might be thinking that if you use Kura Wires data flow programming model, you might be losing the abstraction, losing the more functionalities or flexibilities that you might get from Kura. But for Kura Wires, it's just a data flow programming model, so there is a chance that I would lose lots of functionalities or lots of flexibilities. Actually, no. Kura Wires actually fits in such a position in the stack that I've already seen. It actually uses all its services underneath. So all the layers it can actually access. All the different nodes that the specialized node that we're providing, and also you can even create. So those nodes are actually the components that are already present in Kura. And as I said, that in Kura Wires, we have added lots of extension points. So that if you think that you might need more flexibility than the current nodes offer, you can actually use those extension points and create your own specialized nodes. So that's how we made Kura Wires extensible. And actually, you might be knowing, if you know about Kura, then you might know that we have an Eclipse Marketplace integration. That means that you can create your own plugin for Kura, and you can host it in the Eclipse Marketplace. And anyone who uses Kura in their own installation, they can drag it into their installation, and they can use that plugin. So we actually have taken that advantage. So what we did is, actually that's our vision, we have not integrated so far. What we want is that there can be two classes of developers. One can be the node developers, like the node developers will be responsible for creating nodes, specialized nodes. They can upload the nodes to the Eclipse Marketplace. And there can be another group of developers, another class of developers. I actually call them the IoT application developers. They can actually use those, they can actually consume those nodes from Eclipse Marketplace, use them to implement an IoT scenario using like this kind of data flow graph. So that's what the vision is. So I think within a few weeks, we'll be able to do something with the Eclipse Marketplace stuffs. So now, as I said before, that Kura Wires actually uses all the lower level stacks. So you can see that it's actually, Kura Wires actually sits at the application layer. So Kura Wires uses all the different stacks that actually resides underneath. So along with Kura Wires, we have also incorporated some concept of assets and drivers. And it's actually not part of Kura Wires, it actually uses Kura Wires, Kura Wires actually uses that model, and that's the asset and drivers, but here I'd not be talking about it, because it's the later slides, later on I'll be talking about the asset and drivers. Okay, moving on. So before I move on to discussing about like presenting a complete end-to-end graph, like implementing an IoT scenario using the Kura wires, I would like you to know about the different terminologies involved in Kura wires. The first one is the wire graph, and it's also, I guess, it's self-explanatory. So the wire graph in Kura wires, the data flow graph that we create is actually known as wire graph. So I have an example here. It's actually taken as a complete screenshot from Kura wires. So here you have the end-to-end data flow graph that you create to implement an industrial automation scenario or industrial IoT scenario. And this is known as the wire graph. Now the concept of wire components. So each and every node in the wire graph is actually known as the wire component. So if you consider the same graph that I have shown you before, so here the highlighted ones, they are actually the wire components in Kura wires. Okay, so as I said previously when I started about talking about the Kura wires, the wire component can be a producer of data, it can be a consumer of data, or it can be actually both. So inherently, the wire component has 0 to n number of inputs to another wire component, or it can have 0 to n number of outputs from a wire component. And also, the wire components don't need to have any context-specific knowledge about each other. So this is the reason they actually are completely independent. They don't know anything about each other. They know only what they are processing. So that's the concept of wire component. Now comes the concept of asset. As I said, as we have already seen in the slide, like the updated enhanced architecture with Kura wires, we have the concept of assets and the drivers that the Kura wires actually needs. So this is the asset. So prior to Kura wires, we have actually developed another component model on Kura, atop Kura, and that is called Kura asset model. Asset actually denotes a logical representation of a field device. But an asset is a high-level abstraction. Asset actually associates a driver instance to interact with the PLC. So it would be some kind of like this. So asset associates the driver. Driver provides the implementation to interact with the PLCs or to the field device. And using this high-level abstraction asset, you can actually interact with the field device directly using the driver. So in the context of Kura wires, as I said, that Kura wires actually uses this component model to interact with the PLC. So if you just don't care about what the asset model is, but for Kura wires, assets are a specialized wire components that interact with the transducers, means the field devices. So for example, it can be the Modbus device, S7 PLCs, or OPC PLC, and whatever. So this is the wire component. This is also an asset, as because it associates a driver. This is the association, and it interacts with the PLC directly. So wire component, if it associates the driver, it's known as asset. So there comes the point of wire. So wire is actually the logical connection between different wire components. They are known as wires. So if you consider the same graph here, so the connections, the lines that you see here, like producer to consumer, producer, and so on. So these are known as the wires. Okay. Now finally the terminology is the wire envelope. So wire envelope is a abstract data format that every wire component is actually wrapping the data that it processes and sends it across to the connected components. So it doesn't have proper specification. It's developed in such a way that every node actually opens it, reads it, finds what it needs to do. It knows that it should do this processing task. It reads the data, processes on top of the data, creates, if it produces something on top of that data, it produces it, wraps it with wire envelope, and sends it across to the wires. So this is how we can make sure that every component will never know or will never have any context-specific knowledge about the other nodes, about the other wire components. So just to visualize how it works, so suppose producer is producing here the starting node, it produces it, it creates a wire envelope, is actually sends to the consumers, and then the consumer producer processes it, produces the data again, and it also sends across to the different components. It also produces it there, and it reaches to the final node. So this is how it actually works for the wire envelope. So what we are providing with Kura wires so far. So we're actually providing the basic, or I would call preliminary wire components and drivers. So the first one is the timer. Timer is a specialized component which actually you can configure it with that interval. So it ticks or it fires an event as soon as it actually passes the interval. You can use the timer to define the simple seconds or simple milliseconds and hours and all. You can also use the timer to define your own cron job. So you might be having some kind of like device from which you want to get the data like every 30 days or every 1 week. So you can also use the cron jobs to do that. And then the concept of cloud publisher. You can use the cloud publisher in the graph so that it receives the data, it publishes it to the configured cloud platform. And then comes the concept of the subscriber. So the subscriber is also pretty much same as you can think of. It's subscribed to the data from the cloud platform and then passes it along to the other connected wire components. So why do I care about subscriber? So I actually cared about subscriber because suppose you have two different gateways in two different places. One is equipped with a complete wire graph and industrial scenario implemented and is continuously pushing data. The publisher is actually continuously publishing the data to the cloud. So you have the other component there, so other gateway, which is also equipped with another wire graph, which receives the data. So subscriber can receive that data exactly, which is actually it is sending. It receives the data, it creates a wire envelope out of that data and sends it to the another component. So this is how we can achieve inter-gateway communication between two different wire graphs. Okay, moving on, the DB store, also it's same. Like it receives the data, it stores it to the configured database. So right now it's storing the data in the embedded database that is actually coming with Kura. You can also configure it to store it in a remote database storage as well. DB filter, it's interesting. So according to me, I believe that DB filter is the only thing which through which we can actually achieve edge computing. Because you can think of a graph where you put the DB filter to provide specialized queries, which actually filters the data out of the database, and only the filtered data would be passed along to the connected components. So it's not that the data that you get is passed directly, so it would be no more edge computing. So if you want to do some more filtering, you do it at the edge level using DB filter, and then you can achieve it. And then the simple one is the logger. It just logs the data to the log file. This is actually, I created it because I wanted to have a kind of confirmation that the wire is working properly. So that's how I created the logger. Now the concept of asset. So asset is a high-level abstraction, as I said before. So asset is actually specialized by associating a specific driver. So there will be different instances of driver, but not different instances of asset. So asset associates the driver. So there will be different kinds of drivers that we're providing so far. So we have a Modbus driver, which we have created only for Kura wires. And then we also have OPC-UA driver that we can also use to interact with the OPC-UA PLCs as well. Yeah, that's it for the Kura wires. So now it's actually good to have a kind of demo. But before that, I would like to show you a proper industrial IoT use case that we would be doing it with the Kura wire stuff. So suppose here we have, so this is a factory, I guess it's a plant. So this is a PLC, which is actually running Modbus, and it's connected to the gateway using Modbus RTU. And it's continuously, so we have to create, what we want is we want to get the data. We want to read all the different sensors connected to this Modbus PLC, and then upload it or publish it to the cloud platform. And then we'll have a proper client, dedicated client, through which you'd be able to see the data published to the cloud platform, and we'll be able to actuate, like to send commands and do some more processing on the device actually. So how do we do it using Kura wires? That we'll be seeing now. So I guess I have to connect, yeah. Is it fine if I stay here? Or?
At the other side.
One sec, I'll tell you. Why? I have to change it.
Extended. It's not
How do I change the resolution?
preferences.
System preference, display.
Monitor. This one. Okay.
Just one sec. I'll tell something. And then I'll say.
Close it.
Okay.
Close it.
One sec. Why?
No, it's the other. Close it. Don't care about it.
Okay. One sec. I'll tell and then we'll continue. So here, this is a kind of the web console for Kura. So here you see that we have the wires tab here. So you click on it, you'll get to have the Composer UI, where you actually create the graph to implement an IoT scenario. So what you do is, to implement this scenario, what we do is, we'll first need a timer, because it actually ticks. So here I can provide what is the time that after which it would tick. And then what we need is, we need an asset. So, okay, sorry. But before that, I have to create a Modbus driver instance. Just forget about what I've created. So the Modbus driver that I'll be creating now is this. And I give it a very good name, my Modbus driver. So see, it's actually created here. So here I have the TCPs and all the necessary configurations that's needed to connect to a Modbus PLC. And then in wires, I have to have a timer. Let's call it T. I have to have an asset, which I have to associate it with a Modbus driver. This is the driver instance that I actually need. So this way you can actually have multiple instances of the driver. And the component name, I can call it D or devkit, or maybe Modbus, and I just, okay. So I can wire it this way. And then I can have another instance of the publisher. I can put it here. It's pretty simple. So for the timer, what are the configuration that it needs? So it has this simple and the cron, as I said before. So now it can be 1, like for every 1 second it just triggers. For Modbus, in the Modbus we have a kind of proper section where you provide the different channels. I guess this is the data points that we call in the IoT field, I guess. So for a channel, what would that be? So for a channel, we need a channel, user-friendly channel name. We need to know the type that you should perform the channel. It can be read, it can be write, it can be both. And the value type that you expect out of this operation. So you might expect that the data is an integer or the Boolean, depending on the field protocol. Okay, and the rest of the column that you can see, unit ID, primary table, and the memory address is actually it's actually field related, the field protocol specific. So for Modbus, we need the unit ID, the slave ID, and the primary table. So here it would be the holding registers and all, and the memory address. So that it actually connects to. So for publisher, it actually use we configure everything here in the Kura, the data service and all to connect the cloud service to connect to the cloud platform. This publisher actually attaches, so it injects the instance of the cloud service to itself to use the publisher instance in the Kura wires. So here you see that we have the configuration like do not connect on event and when to do, what to do, like when to exactly publish and when to disconnect as soon as I receive something and what needs to be done. Those kind of logic are actually there in the different auto connect modes, and the rest, which topic to publish and those specific configurations. So this is my local environment right now. So I'm not actually connected to this. So what I would do is, I would like to shift to this, I guess this one. So this is the actual installation that's actually happening. So this is the actual scenario that I have implemented long back. And it's, you can see due to the time constraint, we couldn't do that properly because there are lots of channels involved in the asset, like this many, all the lights and all the toggles you can see here. So the timer here, it triggers every 1 second. The asset reads it, receives the wire envelope. It knows that it needs to perform read and write operation, different read, different write operations on this many channels. And it performs all this, and then it creates a wire envelope out of it and sends it across to the connected components. The publisher receives it, sends it across to the cloud platform. So here we have a client also. So the client receives the data from the cloud platform, and it shows you that this is the dashboard through which the control operator can interact with the field device. It gets the data, like you see that counter is 34 right now. So if I change something here, the wire graph actually gets triggered. So it's actually a little bit slow. It gets 35, 36. I changed it, it gets green, changed it. So now if I want to actuate something, like the LEDs, I send the command, and you see that it gets on, switched on. So this is how the client is actually interacting with the wire graph that we have already deployed at the field. So at the edge gateway, you have created an industrial automation scenario using a simple wire graph, and you can actually interact with it from remote location. You didn't have to code anything for this. So this is the benefit of having Kura Wires in such kind of rapid deployment. This is not even restricted to such kind of easy deployment. You can even create your own different complicated wire graphs where different edge devices also are communicating with each other. They are writing some data getting data from one device, writing to another device. This kind of mapping is also possible. We have implemented that. So pretty soon we'll be writing a I guess the proper documentation of how to read a data from one device, write to another device. So this kind of communication is also possible through the wire graph by creating the wire graph. Yeah, I think, that would be all for Kura Wires. Yeah.
So for now, it looks like the publisher is quite tightly bound to the assumption that the transport protocol is MQTT.
Yes.
Because the parameters were all very MQTT specific.
Yes.
So is the idea that if I want to use a different transport protocol with the backend, that I would implement another publisher node that is specific for that particular transport protocol? Then?
Yes.
Okay.
So you just have to use the extension point to create a specialized component.
And another question, if I now have created this wire model for this gateway, and let's say I have a population of 100 of these gateways.
Yes.
Is there a way to centrally develop these models and roll them out to the...
Yes, you're actually right. That's the vision of ours, So what we want is we can create a kind of cloud parameter where you can actually know that you create the wire graph in the cloud level and then deploy it to the edge nodes even. So that we actually want. So that you can deploy the graph.
Something that you will have in the future.
Yes, we'll have in the future. It's not, I guess, it's not that kind of, I guess, complicated for us to deploy even because we have the Kapua thingy.
So would that then be a feature of Kapua or would
yes.
that be a feature of Everway Cloud?
The Kapua. Yeah.
Are there other questions? Yeah.
You earlier said that these wires allow IoT developers which don't know Java and OSGI
Yes.
to implement new behavior and deploy to the gateway.
Yes.
Now, my question is, if I was coding in Java,
Yeah.
I would have all the features of the imperative language.
Hmm?
And in this graphical notation, I don't see items such as decision gates or joins.
Yeah.
Because they are coming because it's more functional. Why?
It's the base model right now that we have created. So you want more flexibilities on the data to process the data, right? If I'm not wrong. If I have understood you correctly, you want more processing, more power on the data So actually what we want, if you want more processing, there has to be a specialized node which actually gives you more conditional advantage, where you can put more conditions on the data that you're receiving from the upstream nodes. So that's actually also, the plan of ours, so that we can create a conditional component so that you can put it there, put your own conditions there, and then do the processing. That's one part. If you want to provide some kind of Java, so we are thinking of providing kind of Groovy support in the runtime, so that there will be a specialized component, and you write your Groovy code at the runtime. It gets the data from the upstream components. The Groovy starts working, process it there, and then sends it across to the connected component. So that's what actually we want.
Don't you think that having like decision gate rather than Groovy scripts will make the graph more readable maybe? Because otherwise you need to look into the box to find out that this Groovy script is taking a range to another depending on the value.
No, as I said before that we don't have a specific model for the data. So the data model is pretty abstract. So the way, even though you provide a Groovy script or something else to process the data, to provide conditions on top of the data that you receive, doesn't even matter because you don't have a model. The way you read the data, it will be as same as you are just opening something and getting out of it. It's not that you have to read that parameter and then that parameter or that parameter, no. So it's just, we don't have a specific model for the data. So I don't think that will be the kind of thing that we should go for, because if you provide a model specification, it will be difficult to have different implementations for like wire components. Suppose I provide a Groovy script. So suppose I model a component where you can actually provide the Groovy script. It receives the data. It actually doesn't know that how to read it. So that's why the model is pretty abstract, that whatever you provide, you actually know that this is a pretty simple model. You have this chain, just do it that way. Yeah.
Are there any plans to support transaction boundaries in this wired model? Did you say you have a transaction consisting of several consumers or producers, and if one fails, it rolls back the whole transaction? You know what I mean?
Yeah, I understood. So I think so far we have not considered that transaction boundaries. So maybe for later on, it's just a few months of project that we have worked on. So I think later on we might need to consider that transactions to have a proper, like the boundaries for it. Yeah, maybe. Yeah, that would be really nice.
Right, thank you very much.
Yeah.